Hey everyone, and welcome back to the channel. Have you ever wondered if we could predict earthquakes just like we predict the weather? Imagine getting a text alert. Big one's coming in 2 days, time to prep. Sounds like science fiction, right? Well, today we're diving deep into the fascinating and super complex world of earthquake prediction. Is it possible? And if so, how close are we? Let's find out. First, let's get a quick refresher on what an earthquake actually is. Picture our planet's surface, the crust, as a giant jigsaw puzzle. These puzzle pieces are called tectonic plates, and they're constantly moving, grinding against each other. Most of the time, they're stuck due to friction. But the pressure keeps building up and building up until snap. The rocks break. The plates suddenly lurch past each other, and all that stored up energy is released in the form of seismic waves. That's the shaking we feel as an earthquake. So, to predict an earthquake, we'd need to know exactly when and where that snap is going to happen. It sounds simple enough, but the Earth's crust is an incredibly messy and complicated place. It's not a smooth, perfect surface. It's a jumble of different rocks with countless fractures and faults, all under immense pressure and heat. Predicting a rupture in this system is like trying to predict which specific grain of sand will move next in a giant, slowly shifting sand pile. It's tough. For decades, scientists have been on the hunt for reliable precursors, telltale signs that a quake is about to hit. Think of them as the Earth's way of clearing its throat before it shouts. So, what have they looked for? One of the earliest ideas was to look for changes in the ground itself. Before a big quake, the immense stress can cause the ground to bulge, tilt, or stretch ever so slightly. We now have amazing tools like GPS and satellite radar, that's INSAR for the science fans, that can measure these ground deformations with millimeter precision. By monitoring these changes over time, scientists can see which faults are accumulating stress, basically highlighting the areas that are loaded and ready to go. It doesn't tell us when it will happen, but it tells us where the danger is building. It's like knowing there's a lot of tension on a rubber band, but not knowing the exact moment it will snap. Another clue they've chased is something called seismic foreshocks. These are smaller earthquakes that sometimes happen in the days or hours before a larger one, in the same general area. The problem is they're not very reliable. Many big quakes happen with no foreshocks at all, and when a small quake does happen, you have no way of knowing if it's a foreshock to a monster quake or if it's just a small quake. It's only in hindsight that we can say, oh, that was a foreshock. Not super helpful for a real-time prediction, is it? Then there are some more unusual ideas. People have reported strange animal behavior before quakes for centuries. Dogs barking uncontrollably, snakes leaving their burrows in winter, fish jumping out of the water. While there are tons of anecdotal stories, it's been really hard to study this scientifically. Was the dog barking at a squirrel or feeling the P waves? We can't. It's an intriguing area, but so far, not a reliable scientific tool. There have also been reports of changes in groundwater levels, or the release of gases like radon from the ground before a quake. The theory is that as the rock cracks and strains under pressure, it opens up new pathways for water and gas to move. Again, while some links have been found, the signals aren't consistent. They might appear before one quake but not another, making them unreliable for a universal prediction system. So, with all these challenges, where does that leave us? Are we just sitting ducks? Not at all. Not. The focus in seismology has shifted from prediction to forecasting and early warning. Let's break that down. Earthquake forecasting is like a weather forecast, but for much longer timescales. Based on historical earthquake data and our understanding of plate tectonics, scientists can calculate the probability of a major earthquake happening in a specific region over a period of, say, the next 30 or 50 years. For example, they can say there's a 70% chance of a magnitude 6.7 or larger earthquake hitting the San Francisco Bay Area in the next 30 years. This isn't a prediction of a specific date, but it's incredibly valuable information. It's the reason why cities like San Francisco and Tokyo have such strict building codes. This long-term forecasting allows communities to prepare, to reinforce buildings, to practice drills, and to build resilient infrastructure. It saves lives, just not by giving a 24-hour warning. Now, this is where it gets really cool. Earthquake Early Warning Systems, or EEWs. These are real, they exist, and they're saving lives right now in places like Japan, Mexico, and increasingly on the west coast of the US. So how do they work? They don't predict the quake, they just outrun it. When an earthquake happens, it sends out different types of seismic waves that travel at different speeds. The first waves to arrive are called P waves, or primary waves. They travel the fastest, but they're relatively weak and don't cause much damage. You might feel them as a little jolt or a rumble. Following them are the S waves, or secondary waves, and the surface waves. These travel slower, but they carry the destructive power of the quake, the violent shaking and rolling. An EW system uses a network of sensors placed near major faults. When an earthquake starts, these sensors instantly detect the initial, fast-moving P waves. They immediately relay this information to a central processing center. A computer then rapidly calculates the earthquake's location, its estimated magnitude, and which areas will be affected by the more dangerous S waves. This whole process takes just a few seconds. This information is then blasted out as an alert to phones, TVs, and public address systems in the target areas. Depending on how far you are from the epicenter, this can give you anywhere from a few seconds to maybe a minute of warning before the strong shaking arrives. A few seconds doesn't sound like much, does it? But think about what you could do. You could drop, cover, and hold on. Surgeons can stop delicate procedures. Trains can automatically apply their brakes. Elevators can be stopped at the nearest floor and their doors opened. Fire station doors can open automatically. It's enough time to move away from windows or heavy furniture. Those precious seconds can be the difference between a close call and a tragedy. It's an incredible application of science and technology to make us safer. So, what does the future hold? The Holy Grail is still true short-term prediction, that 2-day warning. And scientists are not giving up. The next big frontier is using artificial intelligence and machine learning. Imagine feeding a powerful AI all the data we have, real-time seismic data from thousands of sensors, GPS ground deformation data, historical quake records, everything. The AI could potentially learn to recognize incredibly subtle patterns in this mountain of data that human analysts might miss. The complex interplay of tiny tremors and ground strain that might be the true precursor to a big one. Researchers are already running lab experiments where they simulate earthquakes on small rock samples and use machine learning to predict when they will fail. And the results are promising. The AI is getting better and better at picking up on the acoustic signals, the tiny crackles and pops the rock makes, that signal an impending slip. Scaling this up from a rock in a lab to the entire San Andreas Fault is a monumental challenge, but it's a very exciting path forward. It's a journey from studying the Earth to actually listening to it. So, to sum it all up, can we predict the exact time and place of the next big earthquake? Not yet. The Earth is still holding its cards very close to its chest, but we have gotten incredibly good at forecasting where they are likely to happen over the long term, allowing us to build safer cities. And with earthquake early warning systems, we're using technology to get a precious head start when a quake is already underway. And with the power of AI on the horizon, the dream of true prediction might not be science fiction forever. It's a testament to human ingenuity and our relentless drive to understand and adapt to the powerful forces of our amazing planet. Thanks so much for hanging out and exploring this with me today. I hope this cleared things up. If you found this interesting, do me a huge favor and hit that like button and subscribe for more deep dives into the world of science. Got a question or an idea for a future video? Drop it in the comments below. Stay curious, and I'll see you in the next one.